Now that you have seen an example of dynamic programming in action, let's take a look at another example. The second example we will be looking into is called the common subsequence problem. First, let's try to understand what a subsequence is. A subsequence of a string is another string with 0 or more characters left out. For example, if you have a string A, B, C, D, E, F, then one of the subsequences can be A, B, C, and another subsequence can be A, C, D, E. One thing to remember here is that subsequence and substring are two different concepts. In substring, you cannot have any out-of-order characters. Remember this important fact. All substrings are also subsequences, but not all the subsequences are a substring. So, what is the longest common subsequence problem? Given two sequences or strings x and y of length m and n respectively, we need to find the longest subsequence common to both of them. In this problem, if there are more than one longest common subsequence, you only have to find one. You don't have to find all of them. Here is an example. Let's assume we have two strings x and y, a, b, c, b, d, a, b, and b, d, c, a, b, a. The longest common subsequence or LCS of x and y is BCBA. The notation used in this case is LCS of x and y. Even if it looks like a function, it is not a function. For two strings with a smaller length, it might not be a problem to calculate the LCS. However, if the strings are very long, say millions of characters long, then it will be impossible to find out the LCS without an efficient computer algorithm. One example can be the proteins in the human body are represented using some characters like A, C, T, G, etc. And one protein's representation can be very long. If we want to find out similarities between two proteins, we might want to use our LCS algorithm from the representation of two proteins. This is why we want to find a very efficient algorithm for this problem. We will see a couple of solutions for this problem and find out which one is efficient enough to use in the practice. Let's talk about the brute force approach of LCS algorithm. In this approach, we need to generate all the subsequences of x and y, and then find out whether there exists any common subsequence by taking every sequence of x to see if it is also a subsequence of y. We need to take the longest of subsequences. So what would be the runtime of that algorithm? First, we need to find out how many subsequences are possible for a string x with length m. There are 2 to the power m subsequences possible for x. Each bit vector of the length m determines a distinct subsequence of x. If you are not familiar with the concept of bit vector, let me know. I will explain this in another video. Similarly, 2 to the power n subsequences are possible for the string y. Hence, the total runtime will be exponential. As we all know, the exponential runtime is one of the worst runtimes you can imagine. We need to find a better solution. Next, we will try to solve the problem using dynamic programming technique. As we know, using dynamic programming technique, we can only solve those problems that have two properties: optimal substructure properties and overlapping subproblems properties. The actual LCS problem is a little bit harder for us to solve at this moment. So first we will try to solve an easier version of the problem and then modify our solution to solve the actual problem. In the easier version of the problem, we will find the length of the LCS, and later we will modify the algorithm to find the LCS itself. That means for the two strings here, x and y, we will first develop an algorithm that will give us the length of LCS, and in this case the answer should be 4, because for the string x and y, LCS is B, C, B, A. The length of this string is 4. The first property we need to consider is optimal substructure property. What it means is the optimal solution to the problem will contain the optimal solution for the subproblems. For the LCS problem, how we are going to define the subproblem? We can imagine two indexes, I and j, for the strings x and y, where I is less than m and j is less than n, shown in the picture here. The subproblem is where we determine the LCS for the string x from 1 to I and y from 1 to j. The picture clearly shows that the optimal solution, in other words, the LCS for the string x from 1 to I and string y from 1 to j, is contained in the optimal solution for the two original string x and y with length m and n respectively. Now it is time to find out a recursive solution to our problem. I can assure you, if a problem has optimal substructure property, it will surely have a recursive solution. In general, how do we think recursively? We try to get the solution of a bigger problem from a solution of a smaller problem, right? For our problem, we need to figure out how we can reduce input size for the next recursive call. In other words, how can we reduce string length for the next recursive call? When you have two strings x and y with length m and n respectively, what can we say about the LCS looking at the last two characters of these two strings? In other words, mth character in string x and nth character in string y. Here we need to consider two cases. The first case, the two characters are the same. The second case, the characters are not the same. For the case 1, when two characters are the same, it means that there is an optimal LCS that contains the last character or mth character. For the next recursive call, we can reduce both strings length by one character each and find out the LCS of x from 1 to m-1 and y from 1 to n-1. Finally, when we have the solution for this recursive call, we can concatenate the last character to get the solution for the actual problem. What about the case 2? When the last two characters are not the same, we can say at most one of them can be in LCS, right? Here we can have two subcases. When xm is not in LCS and yn is not in LCS. What can we do about these subcases? We can actually figure out both of the cases and then choose whichever one is longest. So we can take the LCS of x from 1 to m-1 and y from 1 to n, then find out the LCS of x from 1 to m and y 1 to n-1 and figure out which LCS is greater. That would be our final result for the LCS x and y. In this case, we reduced the sequence by one character. Now that we know about two cases, we need to generalize the concept for not only the last character but also each character. And also, we need to store the result in some place so that we can reuse the result later. We will be using a 2D array called C of size m plus 1 by n plus 1 for this purpose. Here m plus 1 is the number of rows and n plus 1 is the number of columns. The way this array is set up, the cell Cij will hold the length of LCS of two string x from 1 to I and y from 1 to j. This means the cell Cmn will contain the LCS x, y. So, if we write a simple recursive program, it will look like the pseudocode here. In the worst case, while looking at the ith and jth characters, you will always make two recursive calls. This will happen when xi is not equals to yj. Now if we think about the runtime of this algorithm in terms of the recursive tree, it might still be asymptotically exponential runtime. Let's take a look at the partial recursion tree of the case where the length of x is 3 and the length of y is 4. In the worst case, the height of the tree can be m plus n. It will happen when none of the characters in string x and string y matches. That means the runtime can be exponential. Can we guess why dynamic programming can help us here? If we take a look at the tree, we can see two overlapping subproblems here. We can use the memoization technique of dynamic programming to reduce the runtime by not calculating the second subproblem but reusing the solution from the first calculation. Now let's talk about the dynamic programming algorithm for LCS. We need to create a table to store the result of the subproblems. The size of the table should be m plus 1 by n plus 1. Each cell of this table represents the distinct subproblem. If we can fill the cells of this table according to the formula here, the last cell Cmn will give us the answer to the result. In other words, the length of the LCS for string x and y. Now let's talk about how each cell represents a subproblem. Specifically, we will talk about the cell C24. This cell represents the length of LCS between the part of two strings of x and y. The first number 2 represents we only considering the first two characters of string x, and second number 4 represents we are considering the first 4 characters of string y. That means the cell C24 will store the length of LCS of the strings b, d, c, a and a, b. Next, we need to find out in which order we will fill up the cells. We will populate the cell in this order. Why? You need to think it yourself. Let's write down the dynamic programming solution of the LCS problem. First, we need to get the length of two strings x and y. At this point, we will create a 2D array called C. The size of the 2D array will be m plus 1 by n plus 1. Next, we will populate all the cells in the first column and the first row with a value of 0. Why? To understand this, you need to understand what a cell Ci0 means. It means we are considering only the first characters from the string x and not considering any characters from string y. For this configuration, there cannot be any common characters because the string y has only 0 characters. That is why the value of these cells are 0. Next, you need 2 for loops to iterate over all the cells in the table. You populate all the cells using the formula here that we described earlier. At the end, you return the result from the last cell. This will be clear when we see an actual example. We will simulate the LCS algorithm for the example below. What is the LCS of x and y? If you look carefully, The answer is BCB and the length is 3. For the two strings X and Y, the dynamic programming table or DP table will look like this. The first step of the algorithm is to populate the first column and the first row with value 0. Next, we will update or populate the cell C11. That means we will consider one character from X, one character from Y. The first character of X and the first character of Y does not match. So we will go to the else case of the if-else clause. That means we will take the max of C10 and C01, which are the left cell and the up cell respectively. Next, while populating C12, we again don't have a match. We don't have a match in this case also, but while populating C14, we have a match. In this case, we will be using the if clause, and the value for this cell will come from the diagonally up plus 1. Similarly, we don't have a match, so we will take the max of left cell and the up cell. Similarly, we will populate all the other cells. Here we have a match, so we will take the value from the diagonally up plus 1. At the end, we populated the whole table and this is the result. The length of the LCS is 3. Now it is time to calculate the runtime of the LCS algorithm. What does the LCS algorithm do? It calculates each and every cell in the 2D array. So what is the runtime? The runtime is how much time it will spend to calculate all the cells. For one cell, we take a look at either left and up cell and take the max of them, or we add one with the diagonally up cell. So in total, the runtime of this algorithm is order of m times n, since we are calculating all the cells in the array. So the algorithm so far calculated the length of the LCS, but not the LCS itself. Now the question is how we can find the actual LCS. While calculating each of the cells value, we know how we calculated the cells value. We used the formula here. A match happens only when the first equation is taken. So we can start from the last cell and go backward. We have to remember xi whenever the value of Cij equals to Ci minus 1, j minus 1 and plus 1. Here is an example. So at this time there was a match. If we start from the end, now we can see the value in this cell 3 is coming from the diagonally up. That means at this point there was a match. That what it means, that character was in the LCS result. So we can do the simulation again. We started from the last cell, at this time we got the value of this cell from the diagonally above cell. So we can say there was a match. That means the character B was in the LCS. At this point there was no match, but at this point there was again match. That means C should be in LCS. No match, again there was a match, and the character B should be in LCS. So this is our result.